Hi everyone, in today's video we will go over how you properly analyze composite beams. Now, what I mean by a composite beam is a beam that is composed of at least two different materials. So for instance, in this example, we'll be looking at a beam that is made up of a steel channel, and inside of that channel is a wooden beam. So the flexure formula that you learned how to use earlier in class tells you how to analyze a beam that is made of one single material. And it's actually not applicable to beams that are made of multiple materials. So in order to analyze a beam that is made of two different materials, we actually utilize a transformation factor. What the transformation factor allows us to do is to transform one of the beams into a mechanically equivalent version of itself that is made of the same material as the other beam. In order to explain what I mean, let's go ahead and actually take a look at an example that shows how we use this problem-solving method. So if we simplify the geometry of the original problem, we can go ahead and actually put our coordinate system right on the face of the beam. And just as we did in all previous beam bending examples, we will make the x direction be in the longitudinal direction of the beam, and the y direction be through the thickness. So on the face of this beam, we have a moment applied about the z-axis of magnitude 850 pound-feet. Furthermore, we have the following dimensions for this beam. The beam is 16 inches long and 4 inches tall, with 1/2 inch thick sidewalls for the steel channel, and the wooden member fills the remainder of the beam. Furthermore, we have the following properties: that the modulus of elasticity of wood is 1,600 ksi, and that the modulus of elasticity of steel is 29,000 ksi. Now the first step in analyzing a problem such as this is to transform one of the materials into the second material. Now for this problem I've chosen to transform the wooden member into an equivalent steel member. Now in order to do this, I need the transformation factor. Transformation factor to convert wood into steel is merely the modulus of wood divided by the modulus of steel, which provides us with a transformation factor of 0.055172, and note that this is dimensionless. Now once we know this transformation factor, we can actually go ahead and calculate what the width of a piece of steel would be in order to have the same mechanical contribution to this problem, and you will note that I maintained the same height. Once this beam has been transformed into a single material, we can actually analyze it just as you would any other beam. And so the first step in this analysis is always locating the neutral axis. In order to locate the neutral axis, we use the familiar equation of y bar equals the sum of y bar for each individual element times the area divided by the sum of the area. And when we work through this equation, we figure out that the neutral axis is located 1.1386 inches above the bottom plane. The next step in analyzing a problem such as this is calculating the moment of inertia about the axis through which we are bending. There are many ways to solve this. You can either sum the moment of inertia of each of the individual parts about the neutral axis, or you can do what I did in this problem, where I pretended I had one giant rectangular beam, and then I subtracted out the missing area. And I also used the parallel axis theorem. Now once the neutral axis and the moment of inertia have been calculated, we can calculate the maximum stress in the steel member. And for the maximum stress in the steel member, we merely use the flexure formula, negative mz times y max divided by the moment of inertia about the z-axis. And when we plug in the values for this, we discover that the maximum stress generated in the steel is at the tip of each of the channels, and it is 1.40 ksi. Once this calculation has been performed, we can go ahead and calculate the stress in the equivalent steel member that is now in the center of the beam. And what you'll see is that as its maximum distance from the neutral axis is the same as for the steel channel in the previous equation, we get that there is the same stress generated at the tip of that member. However, you need to remember that that is the stress for an equivalent piece of steel, and therefore we actually need to transform that stress back into the stress that would be present within a wooden member. In order to do that, we take the stress calculated in the equivalent steel member, and we multiply it once again by our transformation factor. And once we've done that, we calculate the stress that is present in the actual wooden beam. After we carry this procedure out, we find out that the wood only supports 77 psi. So, as the steel is drastically stiffer than the wooden member, it actually supports the majority of the load that the bending moment produces in this beam and shields the wooden beam from the majority of the stress.